So today we're going to classify quadratic spaces over QP. Now remember previously we classified quadratic spaces over finite fields, and their isometric classes are uniquely determined by just two invariants, the dimension and the discriminant. For quadratic spaces over the p-adics, we'll need one more invariant, the Haas invariant. So now let V and W be two regular quadratic spaces over the p-adic numbers. Let's show that V and W are isometric if and only if these three invariants agree. Obviously, we only need to prove this efficiency, so let's do so by induction. For convenience, we're gonna call this common dimension n and this common discriminant delta, and we wanna induct on the dimension. So the claim is that it suffices to show that V and W represent some common element B. So why is this sufficient? Well, because we want to use induction, right? So we want to use the common technique, the same old technique that we have used in all of these inductions. We want to actually write V and W in this form. We want to decompose V and W in this form. So we see that this part is already isometric. Thus, to show that V and W are isometric, we only need to show that V1 and W1 are isometric. And this is where we can use the induction hypothesis. We just need to show that the three invariants agree on V1 and W1. Now, of course, they have the same dimension, because V and W have the same dimension. Let's check that they have the same discriminant and the same Haas invariant. So why do they have the same discriminant? Well, because the discriminant, so how do you compute the discriminant of V? The discriminant of V is just gonna be B multiplied with the discriminant of V1. The discriminant of W is also B multiplied, but now is the discriminant of W1. So then, because these agree, so the discriminant of V1 must be equal to the discriminant of W1. Now, why are their Haas symbols the same? Well, here we want to use the following formula for Haas symbol of an orthogonal decomposition. From this, we see that the Haas symbol for V is going to be equal to the Haas symbol for this space, right, times this Haas symbol of V1 times this discriminant of V1. Similar for the Haas symbol for W. Now, these are the same, right? But then we just showed previously that these discriminants are also the same. These are the same. These are the same. So this means that the Haas symbol of V1 and W1 must be the same. And so, by induction hypothesis, V1 and W1 must be isometric, right? And that means V and W must be isometric. Thus, the whole proof now boils down to proving this claim that there exists a B that is represented by both V and W. And this is why prior to this video we had a video on how to rephrase this in the case of binary form in terms of the Haas symbol. Alright, so now let's show the V and W represent some common p-adic number B. We consider this in two cases. So let's look at the case when V and W are binary spaces. The case when their dimension is 2. This is when we use the previous lemma. To this end, we just need to show that there is some B such that this is equal to SPV, right? Because if it's equal to SPV, it's going to be equal to SPW, because we assume that the Haas symbol of V and W are the same. So we just need to show that there's a B such that is equal to this. In other words, we just need to show that this map is surjective, because SPV can just be 1 or minus 1. So as long as this map is surjective, we are covered. Well, it might not always be surjective. This map actually is non-surjective exactly when minus dv is 1. Observe that the Hilbert symbol of a comma 1 is always going to be equal to 1. So we have to isolate the case when the discriminant is minus 1, and we will discuss this. But we see that if the discriminant is not minus 1, then because this map is surjective, we know we can find some B such that B comma minus dv is equal to this Haas symbol of V and equal to Haas symbol of W. So by our previous lemma, this means that V and W both represent B, and we are done. Okay, how about the case when the discriminant is minus 1? Well, then this is very simple, because then this means that V and W are hyperbolic by our previous characterization of hyperbolic space. So, because they're hyperbolic planes, they will be universal. Thus, we are done with the case of binary quadratic QP space. Now, what if V and W are of dimension greater than or equal to 3? Then here we want to use the following fact, which we'll prove later, which is that the U invariant of QP is just 4. What does that mean? That means the maximum dimension of an anisotropic quadratic space over QP is 4. In particular, that means any space over QP of dimension greater than, any regular space over QP of dimension greater than 4 must be isotropic. In particular, this perp of V, this direct sum of V, with the scale space of W must be isotropic. So there must be some non-zero vector of this that represents 0. But the quadratic form on this is just going to be the sum of the quadratic form, and the quadratic form of the scale space by definition is just minus the quadratic form on W. So we see that there is some vector V and W not both 0, such that this is equal to 0, but that means that QV is equal to Q of W, so we can set this equals to B. Right? And both V and W represents B. Thus, we have proven that both V and W represent some common B. And remember, we used that to split V and W, right? And then apply the induction hypothesis. So, we conclude that over the p-adic numbers, regular quadratic spaces are isometric if and only if their 3 invariants are the same.